Okay. I can't believe I'm doing this. All right. Chemistry review. All right, so first chemistry. If you don't remember, I'm Chelsea, or if you don't know, my name is Chelsea Anorma, and my Chem 102 class challenged me to do some problems in a video, so here I am. So hopefully this is helpful to you. And yeah, so today the topic is empirical and molecular formulas and how do we figure them out. So we're going to do 3 problems, and each of them is kind of in increasing levels of difficulty so that we can kind of get a feel for how to do it. All right, so here's our first one. Adipic acid is an organic compound composed of 49.31% carbon, 43.79% oxygen, and the rest is hydrogen. If the molar mass of adipic acid is 146.1 grams per mole, what are the empirical and molecular formulas of adipic acid? All right, so this kind of problem you'll see come up a lot where they give you mass percents of the compound. So to do that, the very typical way to do it is to start by assuming you have 100 grams of sample. So this will kind of get rid of the percentages and give you an easier number to work with in grams. So start with 100 grams. Start with 100 grams of your adipic acid. So basically that means that out of the 100 grams, because of these percents, we know that we've got 49.31 grams of carbon. We've also got 43.79 grams of oxygen. And we've got, okay, so the rest hydrogen, which means we can just subtract 100 minus 49.31 minus 43.79, and you will get 6.90 grams of hydrogen. Okay, so now that we've got these grams, in order to get formulas, remember that formula for a compound is telling you the mole relationship between each atom that's in the in the compound. So now we've got masses, but the masses aren't going to tell us much. We're going to need to get to moles. So next step, convert all of these into mole ratios. All right, so let's calculate moles of each atom. All right, and this is pretty basic. All you need to do is take the grams that you figured out from the percents for each atom and divide by your molar mass. Remember, of course, that you always want your units to cancel out. And if you do that, you should get 4.1054 moles of carbon with, let me just double check, 4 sig figs. Okay? All right, oops, my light fell down. And that's not gonna work. Okay. You know what? It's fine. You can see, right? Okay, cool. So we've got, all right, so we've got our moles of each atom. We've got, or so far we've just got moles of carbon, but for hydrogen and oxygen, you're going to do exactly the same thing, right? You're going to take 43.79 grams of oxygen, and then you're going to divide by 15.99, because that's the molar mass of oxygen. And same for hydrogen. So once you've done all that, you're going to get to these numbers. So 2.737 moles of oxygen, and 845 moles of hydrogen. All right, now that you've got these moles, we need to get the ratios of the two. So the way you want to do this is look at the amount of moles you have for each atom and find the smallest one. In this case, it's oxygen, right? So we're going to take the smallest mole amount and divide everything else by that amount. So in this case, it's 2.737. So everything is going to get divided by 2.737. Yeah. Okay, so once you've done that, you'll get out a ratio. So in this case, it's okay to kind of estimate, but what this comes out to is about 1.499. This comes out to 1, obviously, and this comes out to 2.5009. Okay, so obviously these aren't whole number ratios, so you've obviously never seen a compound formula that has, fractions in it. So to fix that, you multiply it by whatever smallest number you can use to get whole number ratios. In this case, it's pretty obvious. You've got 0.5s, so you're going to multiply by 2. So once we multiply this by 2, all of them, of course, got to keep the ratio the same, you're going to end up with 3, 2, and 5. So that gives you the empirical formula. So the empirical formula is C3H5O2. All right, so that's how you get to the empirical formula. But of course, we're not done. So do check on quizzes or whatever. Make sure you're getting the right thing. So in this case, they want both. They want the empirical and molecular formula. So the empirical formula is the lowest whole number ratio relationship between these atoms. But for the molecular formula, in order to find that, you're going to need a little bit more information. In this case, it's going to be the molecular mass, or sorry, the molar mass of the compound. So that was given to us here. So we know that we have 146.1 grams per mole. So using that, we can determine what the molecular formula is. So let me get rid of all this. All right, and you just do this by simply comparing what your empirical formula weight is to the actual molar weight. So if you get the empirical formula weight, you do this by just going to your periodic table and seeing what the molar mass of each compound is and multiplying it out. So in this case, it will be 3 times 12.01 for the carbons, plus 5 times 1.008 for the hydrogen, plus 2 times 16 for the oxygen, and you come out with 73.07 grams per mole. Okay, so obviously that doesn't match with what the molar weight that was given is. So you need to multiply it by a whole number in order to get to that ratio. If you're good at math, or at least better than math than me, then you can probably already tell that you just need to multiply this by 2 to get the right molar mass ratio. But if it's a little bit more complicated, or you're also not that good at math like me, then what you can do is just divide it in order to get the right relationship. So you would divide the actual molar mass by the empirical formula mass, grams per mole, and that would give you somewhere around 2. All right, and now that we've got that, we know to get the actual molecular formula, all we need to do is multiply the entire empirical formula by 2. And so that comes out to C6H10O4. And there you have it. That's the empirical and molecular formula for adipic acid. All right, next chemistry. So we are going to ramp up the difficulty a bit now with this next problem on vitamin A. So vitamin A has a molar mass of 286.4 grams per mole and a general formula of C6HYE, where E is an unknown element. If vitamin A is 83.86% C and 10.5% percent H by mass, what is the molecular formula of vitamin A? All right, so a couple notes for this problem. A couple people were tripped up by this general formula thing here. So what this general formula is doing is it's standing in for your molecular formula, or actually your empirical formula as well. So there's no subscript for E, as you can see right here, whereas there's different subscripts for C and H. So what this is indicating to you is that there's only 1 mole of E for every 1 mole of C6HYE, you know, for every 1 mole of vitamin A. So that will be important later on. And also, there are several ways to go about doing this problem. You guys kind of encountered this as you're working this out yesterday. So I would accept any method that worked on a quiz as long as I can follow it. So be sure to show all your work and make sure you're using the mole relationships the appropriate way. All right? Okay, so here's what's probably the most straightforward way, and it's a little bit different. So what I'd suggest actually is assuming 1 mole of vitamin A. So assume 1 mole of vitamin A. So what that means is you've got 284.6 grams of vitamin A. Because obviously of the molar mass. It's 286.4 grams per mole. So if you've got 1 mole, you've got 284.6 grams of it. So from there, we can figure out the moles of all the other things. So find moles of C and H. Okay. So for this, you start off with your grams of vitamin A. So you've got 284.6 grams of vitamin A. And then here's a little bit of a tricky part. You're going to use this relationship that every gram of vitamin A has 0.8386 grams of carbon. So where did this magical relationship come from? It's actually just from the percentage, right? So because this is a mass percent, what this is saying that every gram of vitamin A, 83% of it is carbon, right? So when you convert the percentage into a decimal format, that's what it looks like. So this is just coming from the percentage. So every gram of vitamin A is 0.8386 grams carbon, all right? So that's where you're pulling from. This is where you're pulling that number from. And then we want to get to moles of carbon, right? So then you use your good old-fashioned molar mass from the periodic table, and you're at moles. Okay. So this comes out to something like 19.9979, which is cool, but this basically means you've got a number of about 20. Okay, then you do the exact same thing for hydrogen. So this was finding carbon here. Now let's go for hydrogen. So again, starting from your grams of vitamin A, you then use your percentage, 10.56% of hydrogen, to say that every gram of vitamin A has 0.10556 grams of hydrogen. Then molar mass of hydrogen gives you the moles of hydrogen. In this case, it turns out to be right around 30. Okay. So you might have thought, like, well, I could have done this with like 100 grams per mole of vitamin A, right? Why did I have to start with 284.6? So the nice thing about starting out with a mole of vitamin A, it means that you can relate this directly into the molecular formula, because what we're saying here is that every 1 mole of vitamin A has 20 carbon atoms. and every 1 mole of vitamin A has 30 hydrogen atoms. So this directly relates into the formula relationships, right? So we know that that the empirical formula, or I should say molecular formula, is going to start off with C20H30, and then of course our E. So we know this because we know that every mole has 20. So we know that it's an actual relationship there. So every mole has 20 of carbon and 30 of hydrogen. Okay, so that's pretty nice. Now we need to figure out what E is. And the good news is that we're pretty close. We just need to use the molar mass to figure out what E is. So to do that, let me get rid of this right here. So to figure out E, you need to find its molar mass. So we're already pretty close because we know that our molecule is C20H30 and E. So we can use subtraction to figure out what E is. So we know that the molar mass is defined the mass of 1 mole, right, which we already figured out from the last problem, is going to equal 20 of carbons plus 30 of hydrogens, and then E, which, as you recall from our note before, because there's no subscript on here, that means there's just 1 of E here. So whatever it is will be the element's molecular weight, which we can figure out from the periodic table. All right, so this comes out to obviously the given 286.4, and then everything else here ends up being around 270.44 grams per mole plus E. Then it's just a quick subtraction, and we know that the molar mass of E is equal to 15.96 grams per mole. And if you look up the periodic table, we know that oxygen is around 15.999, so that is closest to oxygen. All right, so that means our full equation, or formula I should say, is C20H30O. And there you have it. All right, so that was using the assumption of 1 mole of vitamin A. But, you know, this is a little bit unusual, although honestly you could do all the other problems assuming a mole as well. And it's just that then you would have to go backwards to find the empirical formula. But what if we tried the usual assume 100 gram strategy? Well, that could work too. It just might take a little bit more thinking. All right, so if we assumed 100 grams of vitamin A, then that would mean that we've got 83.86 grams of carbon, 10.56 grams of hydrogen, and 5.58 grams of E. So all these two are just directly from the percentages, and E is just by subtraction, right? So we know we have 100 grams total, so the leftover is E. All right, so we go through our usual steps, right? Calculate the moles of each atom. So doing this the normal way, we would go with, okay, we've got 83.86 grams of carbon. We use the molar mass from the periodic table, and we'd end up with 6.982 moles of carbon. So we go along, do the same thing with hydrogen. So we get 1 mole hydrogen, 1.008 grams of hydrogen. So that gives us 10.476 moles of hydrogen. All right, so we're all going along really well. The only problem is now we're going to get to the 5.58 grams of E, and we're going to realize, wait, I don't know what the molar mass of E is because I don't know what it is, right, on the periodic table. So how do we figure this out? So we can do a little bit of thinking on this. So we know that we figured out this percentage, right, by subtraction, right? So we know that vitamin A is 5.58% of E. So that means that 5.58% of vitamin A's mass is equal to the molar mass of E, okay? It's a little bit of a little jumping through the hoops there, but yeah, so what you would then say that, okay, I know that this is the total molar mass of A, and I know 5.58% of that is E. So we'd multiply by the decimal version of 5.58%, and what we'd end up with is 15.98. Wow, that looks familiar. That looks like the molar mass of oxygen. Okay, so in that way, now we know that when we go down here, for E, we're actually replacing that with oxygen, and we're using the molar mass of oxygen for the rest of the calculations. And here's 1 mole of oxygen, and that comes out to 0.34877 moles of oxygen. Okay, so now we do the exact same procedure, right? We find the smallest amount of moles, which in this case would be the moles of oxygen, and we divide all the other numbers by it. So everything gets divided by 3,487. This gets divided by 0.3487, and this. And what we'd end up with would be basically, all right, let's see. So yeah, when we go ahead and do this division, you'd end up with about 20 for carbon, we'd end up with about 30 for hydrogen, and obviously just 1 of your oxygen. And so you get the exact same relationship, C20, H30O. All right, so that's basically a different way to do the same problem. So like I mentioned, you can do whichever route makes sense to you. You've just got to show all your work, just like I'm doing right now, so that I can follow it, and you can get all your points on your quiz. All right. Next and final problem. So this is a problem that a lot of you guys have problems with yesterday. A lot of folks got stuck on it. That's okay, because this is a pretty challenging problem. It's one of the challenge problems at the end of this chapter. So don't worry, we'll get through it. So this one says a compound contains carbon, hydrogen, nitrogen, and oxygen. Combustion of 0.157 grams of the compound produces 0.213 grams of CO2 and 0.0310 grams of H2O. So that's one reaction. In another experiment, it is found that 0.103 grams of the compound produces 0.0230 grams of ammonia. What is the empirical formula of the compound? Okay. So the most empirical formula problems start out giving you a mass percent, and then you work from there. But the challenging thing with this problem is they're actually asking you to come up with the mass percents first, and then go on with the rest of the problem. So to do that, you're going to have to analyze the 2 different reactions that are going on here. So you want to think of each reaction separately, and don't worry too much about getting all the details right. For today's lectures material on stoichiometry, obviously we want balance equations, you want the mole ratios of everything. That's fine. But in this case, you don't have to worry about that because we're doing mass percents. All we care about are the mass percents. All right? So the first one that they described here was a combustion. So you take this this compound, which all we know is it has some amount of carbon, hydrogen, nitrogen and oxygen in it. You take that, you combust it, you burn it, you produce CO2, you produce water, and probably some other byproducts because the nitrogen has to go somewhere. But we're not too worried about that because we're mostly looking at the grams of stuff. So we know we've got 0.157 grams of this compound going in, and then 0.213 grams of carbon dioxide coming out, and 310 grams of water coming out. Okay, so for these reactions, I didn't write it up here, but it's stated in the problem that you need to assume that all of the carbon and hydrogen from the combustion reaction are ending up in the carbon dioxide and the water, respectively, okay? And then there's a second problem, right, where you have another sample of this mystery compound, and it's going to ammonia plus other byproducts. So in this one, we have a different starting amount. So we've got 0.103 grams of our mystery material, and it's going to 0.0230 grams of ammonia. And in this case, you're assuming that all the nitrogen from this mystery compound ends up in the ammonia at the end of the reaction. Okay? So we're going to think about these two reactions separately and find the mass percents for each atom. So let's start with the combustion reaction first, actually. So in the combustion reaction, we're going to find the mass of carbon first. Okay. So for the mass of carbon, you start out with what you're given. You know that 0.213 grams of CO2 contains all of the carbon that was in the 0.157 gram sample, okay? So we need to figure out how much carbon that is. If you figure out the molar mass of CO2, you'll find that it's 44.01 grams of CO2 for every 1 mole of CO2. And then you use the mole ratio of CO2 itself and say that for every mole of CO2, we're just going to get 1 mole of carbon out. So this looks like it's not super necessary, but it can be relevant if, this is not a 1-to-1 ratio. And then finally, because we're looking for mass percents, right? We're looking for the mass of carbon. We're going to convert this to grams. All right, so that should all cancel out and give us 0.0582126 grams of carbon. All right, so we're assuming that this is all the carbon that was in this sample. So if we're assuming that, that means we can calculate the mass percent of the carbon in that sample. So the percent of carbon is equal to that mass of carbon that we just found over the mass of your sample that you're using, which is 0.157. And of course, multiply by 100 because we want a percentage. And what you'll get is 37.0% carbon. All right, so now we got a mass percent for carbon. Let's move on to hydrogen. Okay. All right, so hydrogen, so percent carbon, and then now we're going to do percent hydrogen. So first of all, the mass of hydrogen. So again, we're assuming that all the hydrogen in our sample got converted into water. So we're going to take our mass of water, which is 0.0310 grams of water, we're going to divide by the molar mass of water, which is 18.02 grams per mole. And now you see the mole ratio actually matters, because for every mole of water, you actually have 2 moles of hydrogen. So if you don't remember that, that could make you off by a factor of 2. And then finally, we're going to get the actual grams using the molar mass. Okay, so that will get us a pretty small amount of hydrogen. So 3.468 times 10 to the negative 3 grams, that looks terrible, 10 to the negative 3 grams of hydrogen. And then we get percentage, just like that we did for the carbon. So the percent of hydrogen is going to equal the mass of hydrogen that we just found, divided by the total mass in our sample, which is 0.157, because we're still dealing with that first sample. And then times 100%. So that will give us 2.21% hydrogen. Okay? All right, so we got carbon and hydrogen from this first one. Now, to find nitrogen, we're actually going to need to switch over to the second reaction that we talked about. So let's go back to that one. Okay. So the second reaction starts off with the same material, our mystery compound here, but now it's going to ammonia plus some other stuff. So again, we're going to assume that the whole sample, so now remember this is a different sample because it's a second experiment. So they gave us a different mass. So make sure we're using the right one here. 0.103 grams of the sample is going to 0.0230 grams of ammonia. But we can still make the same assumption, because they told us we could, that all of the nitrogen here, basically all of the ammonia contains all of the nitrogen that was in the original sample. Okay? So we're going to do the exact same procedure. We're going to start with our amount of ammonia here. We're going to divide by the molar mass of ammonia, which is, I have in my handy dandy notes. Okay, 17.03 grams of ammonia in 1 mole of ammonia. Then we do the mole ratio. In this case, it's pretty easy because it's 1 mole of ammonia, just has 1 mole of nitrogen. And finally, get to the grams that we want. So 1 mole of nitrogen is 14.01 grams of nitrogen. Okay? So that'll give us 0.01892 grams of nitrogen. Okay, so percent of nitrogen, same route as before, just remember to use the right sample this time. So you have 0.01892 grams of nitrogen that we just discovered, and we're going to use this sample, not the other one, this sample as our total mass times 100, and that will give you 18.3% nitrogen. Okay, so we figured out what carbon, hydrogen, and nitrogen's mass percents are. The last one is oxygen, but again, like other problems we've done before, you can figure this out by subtraction. So you don't have to use the any of the combustion or other reactions for that. So we'll just subtract, and now we've got finally all the percent masses that we need to get the formulas. Okay, So just to reiterate, we don't need this anymore, but we know now that we have percent masses for each atom. So for carbon, the percent mass is 37.0. For hydrogen, the percent mass is 2.21. And then for nitrogen, the percent mass was 42.5%. What? No. I let the cat out of the bag. Shh. Okay. So it's actually 18.3%. And then when you subtract all those from 100, you'll get oxygen, which is 42.5. Okay. So now we have all the percent masses of everything. You can continue the problem on as normal by assuming 100 grams, okay? So same procedure, assume 100 grams, convert everything to moles, divide each of the mole numbers by the smallest mole number to get a ratio of everything, and then get whole number ratios. So the only tricky part with that is, I'll let you work out that part on your own, but I will show you the tricky part of that problem is eventually you're going to get ratios that are not whole numbers initially. So when you divide everything by the smallest number of moles, you're going to get ratios that look like this. So carbon is going to be 2.35. Nitrogen will actually be the smallest, so it's just going to be 1. Hydrogen, the ratio is going to be 1.67. And oxygen is going to be 2.03. So when you're trying to get this to whole numbers, initially you might think, oh, I messed up because these don't look like I can, multiply them by 2 and get whole numbers. So do look out if sometimes that means you messed up, but if you notice 0.3s and 0.6s, that's a pretty good indication that you can multiply by 3 to get your whole number ratios. So that's exactly what you'll do here. You'll multiply everything by 3, and then the final answer that you will get is that our compound is C7H5N3O6. All right? So that, super long problem, but that is the answer that you should get. So try those parts on your own, but like I mentioned, as soon as you get these mass percents, everything else works out just like a normal problem. All right? Well, thanks for joining me on this chemistry review. Hopefully you found it helpful, and yeah, so Ryan, this is for you. So remember, you owe me 7 subscribers, so I'll be watching you. So yeah, I guess now that I'm a YouTuber, I got to do the whole thing. Don't forget to like, comment, and subscribe. Leave a comment down below. Ring the notification bell, all that stuff. Remember that we are back Mondays and no, hold on. When are we meeting? Oh yeah, we're here every Wednesday and Friday in Noise Laboratory, and I'll see you on quiz day. Bye.